Hey there, this is a video for my grade 10s. This is the second lesson in chapter 4, Roots and Powers. And we are going to take a look at 4.3 and 4.4 today. And this is, why don't we actually introduce this? We'll say in this section, we learn the algebraic / arithmetic rules for working with radicals. Cool. And while we're on the topic of that, I'm trying to save some space here if you know why I'm writing so small. Let's start by saying that radicals follow the bedmass rules of B for brackets and E for exponents. It's probably pretty obvious why they'd follow the brackets rules. After all, when you put something under a square root sign, it looks like you've put it in a bracket. But the E is interesting. Why do they follow the same rules as exponents? Well, actually, that'll be made clear later on in this video. But first of all, let's start with what we call the multiplication property of radicals. And again, I'm trying to get as much into here as I can. So I'm actually going to kind of start it up here where I've given myself a little bit of room. And I'm going to say that if I'm multiplying two radicals, the square root of A times the square root of B is equal to the square root of AB. And I'm going to put that into a highlighted or put a circle around it because that is kind of the most important multiplication rule. I could even show you for an example of that. Suppose we had the square root of 4 times the square root of 2. Well, that would be, oops, not 2. Sorry, thinking about the next step. I meant to say the square root of 4 times the square root of 9. That's what I meant to say. Well, according to this rule, I could times the 4 and the 9 together, and that should be the same as the square root of 36. Is that true? Well, let's see. The square root of 4 is 2, the square root of 9 is 3, and the square root of 36 is 6. So 2 times 3 is 6. Yep, that rule has to be true. So it's true for perfect squares, and it would be true for any two things that are under a radical sign. And in this case, you could kind of say that the two radicals here are behaving very much, well, like brackets, where we just have, it's like saying that 2 times 3 is the same as saying 2 times 3 in one bracket. And along the same lines of that rule is this rule here. A root B is the same as saying the square root of A squared B. So, as an example of that, suppose I had 3 times the square root of 2. Pause the video for a second, see if you can write down what I'm going to write down. Make sure you do it in pencil in case you don't get the same thing I do. Did you guess what it's going to say? There's probably some people here who think I'm going to say the square root of 6, but it's not the square root of 6, right? Because it's A squared times B, so it's actually 18. Why is it 18? Well, because it's like saying the square root of 3 squared times 2. 9 times 2 is 18. So this is another important rule for how radicals work. Now I'm going to write down something that isn't a rule. Make sure that if you understand these two multiplication properties, make sure that you don't mix them up with this. So I'm going to put note. Note. Square root of A plus the square root of B does not equal the square root of A plus B. Well, why not? Well, first of all, I can prove to you that for sure it can't. Again, I'll use 4 and 9. The square root of 4 plus the square root of 9 does not, under any circumstances, equal the square root of 13. Think about it. That's 2. That's 3. and the square root of 13, I don't even know the square root of 13 off the top of my head. It's 3.6 something. It's an irrational number. And 2 plus 3 makes 5, not 3 point something. So clearly, this is actually one of the more common mistakes people make with radicals, is they think they can just add them together. So how come I could combine those, but I couldn't combine these? And this is where radicals are behaving like exponents. Because hopefully, if you guys remember your grade 9 exponent laws, let me just get off the page here and make a point. You should remember that if you had, say, for example, 2 to the 3 times 2 to the 4, I can add those exponents and say that it's 2 to the 7. But 2 to the 3 plus 2 to the 4, there is no law that allows you to combine those two numbers. There's no power law for addition. It's the product rule. And that is why radicals sometimes behave like exponents. They follow the same rules. And we'll learn more about why that is coming up. Next, we're going to be doing some simplify. Now, before we get into simplifying, I just wanted to talk a little bit about what does it mean in math to simplify something. What do we mean by simplify? So, for example, hey, look, I made some memes. Let's scroll up to this one. There we go. I'm gonna put that one on a math blog that I belong to, and see if people like it. I gotta admit, I probably couldn't hum you a Drake song. This is as much as I know about Drake. But why do we consider this a better answer than that? Well, because we consider it simplified, right? It's simpler to say 1/2 instead of 10 over 20. That's simplified. Now, simplification is an interesting thing. It's not just for fractions. Obviously, we would take something algebraic like this statement here, and we would say that's not simplified because those two things are like terms, so it's simplified if I put it together. We would generally say something like x plus 1 squared isn't simplified because I can expand that bracket into x squared plus 2x plus 1. So simplified, the argument could be made that this looks simpler than that, but this is the factored form and this is the expanded form, and generally we consider this form simpler. And something like that's going to happen to us with radicals. It's going to feel like we're actually making it more complicated when in fact we're making it simpler. Simpler is in the eye of the beholder. Let me go back to my meme for a sec. Fractions actually, I don't know if you know this or not, but this is actually going to come up a little later too. Think of 2.5, of course, as a mixed fraction, right? Sometimes you would say a mixed number, but you can actually call that a mixed fraction because it's got a whole part and a fraction part. Well, you know that that's the same as the improper fraction. (5 over 2), but this is simpler in some cases, right? When you're doing junior high fraction calculations, this would be the simpler answer. But now that you're doing algebra, we actually kind of prefer this answer when we're equation solving. Of course, if you had the answer 10 over 4, that's still not simplest form. You'd have to change it to this because, again, it's simplifying fractions. But this, to most people, the improper fraction is the simpler form. And one thing that's really interesting in the history of fractions, this, of course, 2/3, for example, as a number, that didn't used to be considered the simplest form of that fraction. I know you're probably going, well, there is no common factors of 2 and 3 besides 1, so how could I reduce it or simplify it anymore? Well, for example, in ancient Egypt, they call this Egyptian fractions. 2/3 simplifies if you call it 1/2 plus 1/6. That's the simpler way to do it. Now that one might be kind of obvious, but here, tell you what. See if you can figure out how you'd simplify that. First of all, do you get why they consider this simpler? Because they would call this a vulgar fraction. Oddly enough, that's a term that existed even for fractions right into the Victorian era in the late 18 and early 1900s. So this would be a vulgar fraction rather than a proper fraction, and these were what the 1800s would have called proper fractions, and of course the Egyptians would have called that simplified. To them, this is simpler than that. because they liked the idea that all fractions are expressed with 1 as their numerator. And the fact that you have to express this one as a sum to do that doesn't bother them. And what's interesting is, again, that one, give it a try. Did you try it? Pause the video and try it if you can. It's 1 over something plus 1 over something. Give it a shot. Did you get it? Half plus a quarter. That one's probably fairly obvious, just like this one was probably obvious. But if you try doing tougher fractions, 3/8 is maybe not even as obvious. It's actually 1/3 plus 1/24. And then when you start getting even more prime in your denominators, like 3/7, if this was obvious and this was obvious, and this one you could do by thinking about a little, it takes quite a bit of arithmetic to figure out that that's actually a 1/3 plus an 11th plus 1/231. But as ugly as that looks, the Egyptians would have considered that simplified. So again, for my next meme, I'm going to post this one up and see if people understand what it means. There is actually, by the way, a really neat algorithm that you can use to figure out this quite quickly. I didn't remember it off the top of my head. I had to go look it up, but it's the same. The algorithm is actually named after the same guy that I'm sure we've talked about before, Fibonacci's algorithm. We'll get you that. If you feel like Googling Fibonacci's algorithm, you find a neat way to find Egyptian fractions, which I've always found kind of fun to play with. Anyway, that is a little off topic. What does it mean to simplify this radical? I mean, doesn't that look as simple as it can be? Actually, it isn't. And the reason it isn't is because there is a perfect square factor in that number. In fact, there's a couple. 48 has a 4 in it, but it also has a 16 in it. And 16 is the largest perfect square factor. So now that I know this, I go back to this rule here and I use it backwards. If this thing is the square root of a times b, I can split this up into it being the square root of 16 times the square root of 3. And I know what the square root of 16 is. It's a whole number. It's 4. So this is the simplified answer. So once again, back to my meme. That's there. This is the last one I'll bore you with. I find that cute. Sorry if you think it's cheesy. And oops, that's not what I wanted. There we go. So example 1 is 4 root 3, and again we would call that the simplified answer. Okay, so to a mathematician, this is simpler than that. And whether you like that or not, that's what you have to get used to be able to work with radicals in modern mathematics. So let's do a couple more of those. If that was really easy for you to understand and follow, by all means feel free to pause the video and try these for yourself. Did you try them? All right, let's see. What's the biggest perfect square in 40? Well, 40 has a 4 in it, and that's it. The next perfect square after 4 is 9. There's no 9s. Then there's 16. There's no 16s. And then 25. Nope. So it is going to be square root of 4 times 10, which is 2 times the square root of 10. Remember in math, I guess I should have, maybe I'll put a note to this on here. Remember that this means 4 times the square root of 3, and you don't need a symbol. And the same way, think 2x means 2 times x, right? So you don't need symbols when you just go 4 root 3. You know that means 4 times the square root of 3. And this one is 2 times the square root of 10. All right. If you didn't get root of 40, pause the video and try root 72. Did you get that the biggest perfect square in that number is 36? So this is the square root of 36 times 2, which is equal to 6 root 2. Now, if you had looked at 72 and went, aha, I know what the biggest perfect square is. It's the same here. It's 4. You might have gone, oh, okay, so it's actually 4 times, and then, oh man, what would it be? 4 times? 4 times 18. There we go. I had to think about that. Then you'd have had 2 root 18. And notice that's not the final answer. That's not as simplified as this is, because why not? Because 18 also has a 9 in it. So then the 9 comes out, and that becomes 2 times the square root of 9 times the square root of 2, which is like saying 2 times 3 times root 2, which is 6 root 2. So even if you don't get the biggest perfect square number, as long as you keep looking after step 1, you'll eventually get to the right answer. It's a little like back in junior high. If I had asked you to simplify 12/36, and you'd have gone, aha, they both have a 6 in it, therefore it's 2 over 6. Well, if you stop there, you're wrong. If you realize that, oh yeah, there's still a 2 in those two numbers, you can get to the final answer. So it's the same idea here. This, of course, is the optimal way to do it, to find the biggest possible perfect square in the number. But if you accidentally stop before you find the biggest one, you can still find your way to the simplest answer. You just have to do a little more work. So, more examples. Simplify the following radical. What do you notice that's different about this one? Yep, this is a cube root, not a square root. So I am looking for the largest perfect cube in 24. And, well, let's see, 1's a perfect cube, and then the next one after that is 2 times 2 times 2, which is 8. And then the next one after that's bigger than 24, however, so which is 27, so it's already got to be 8. So this is 8 times 3, and so that's like saying it's the cube root of 8 times the cube root of 3. And here's where you have to, if you're one of those people who writes kind of messy, you got to be very careful. So this is actually going to be, the cube root of 8 is 2, so this is 2 cube root 3. And when you write that, you got to make sure that that 3 is definitely kind of to the right of the end of that radical symbol. You can't make it look like the 2 has a cube on it. It's not 2 cubed times the square root of 3. It's 2 times the cube root of 3. So I make sure that my 3 is definitely to the right. Sometimes I even kind of exaggerate that just to make sure it kind of tucks in there. I don't put it too low though. It is supposed to be up high. So you have to be kind of careful with the way you write. And once again, that is my simplest form. Okay, one more time. See if you can do these. Can you find the biggest perfect cubes in those two numbers? Pause the video and I'll let you try it. Did you find them? Okay, let's see. 96. Well, everything has a 1 in it. That's not going to simplify anything. Does 96 have an 8 in it? I don't know. Let's see. 8 goes into... Yeah, it does. 8 goes into here once with a 16 left over. But is that the biggest perfect cube? Let's see. Let's make a list of our perfect cubes, shall we? There is 1, 8, 27... 4 times 4 times 4 is 64. And then, yeah, notice that we've already, the next one's already going to be 125. So we've passed 96. So the only thing that goes into 96 is this 8. So, yep, it is 8. So it's going to be the cube root of 8 times. Now, 8 goes into 9 once and into 16 twice. So there's no perfect cubes in 12. So that's going to be the cube root of 8 times the cube root of 12, which is going to be 2 cube root 12. Can I point out to you that these two steps here probably won't be something that you do every time as you get better at these. Once you get kind of better at these and your number skills kind of catch up to your understanding, you'll be able to just jump from there to there. All right, next. How about 108? What's the biggest perfect cube in 108? Let's go back to our list. Does 8 go into 108? No, it doesn't actually. Does 27? Actually, yes, it does. 27 times 4 is 108. So this is the cube root of 27 times 4, which is the cube root of 27, which is 3, times the cube root of 4, which isn't going anywhere. So that's the simplified answer. All right. Now, definition time. What we've been doing is we've been taking our entire radicals and turning them into mixed radicals. So entire radical would be, for example, a sum radical to an x where the number out here is 1. So the entire value of the number is contained in the radical. And a mixed radical is when you have some sort of coefficient in front. So you have a product, which is the answer to a multiply, of a coefficient, factor, and a radical factor. And again, this is what we call the simplest form of a radical. So let's go back. So our very first example was, of course, an entire radical would be the square root of 48. And a mixed radical, instead of the square root of 48, again, the 16 came out of here and made it 4 root 3. Okay. Now you might be wondering, well, what's the n value here? I didn't bother writing it. Well, remember that just like I don't bother writing a 1 in front of something when I know it's there, right? In algebra, you never bother writing 1x. You just write x and you know that there's a 1 there. The same thing is true with square roots. A square root has an index of 2. I just don't bother to write it down. So as soon as I see square root, I know that it's, as soon as I see a radical without an index number, I know that it's a square root. But as soon as I put a 3, now it's a cube root. And that, of course, is a 4th root and a 5th root. You can have any number you like as a root. You'll even learn in future grades that this doesn't even have to be a whole number. Wacky stuff. Okay, so there's the first couple pages. Now, on the next page, I'm sad to report, I'm embarrassed by the fact that every single instruction on this page is wrong. Take out a pen and notice this is already, this is already a mixed radical. These are asking us to go backwards, and this is supposed to say an entire radical. And I didn't catch this before I sent this page to the printer and scanned it and put it into onto my blog. But every single instruction on this page has that mistake. So I'll have to fire my secretary. That's all there is to it. All right, that's a joke. I don't have a secretary. My dad had 2 secretaries when he worked a very big, important city job. I used to get one of them to type my essays when I was your age. It's good to be the boss's kid. An entire radical. There we go. Ha! Okay, so write the following as an entire radical. So basically we're going to do the opposite of what we just did in the first few examples. So I need this 4 to go under the radical, so I have the entire value of this number in the radical. So let's see what we can do with that. 4 is like saying, well, here's the way I think about it. The 3 is under here, and the 4 becomes its own square under the radical, because I'm basically back to this rule here, right? This is equal to that. So if that makes sense to you. So that's going to be the square root of 16 times 3. And hey, we've seen this one already. It's our old pal, the square root of 48. And that is now an entire radical. This is not the simplified form, but we might want to change it to this form because we're going to do something algebraically with it or arithmetically with it. In math, anytime you learn an operation, you should learn how to undo that operation. So this is us making it a complete or an entire radical. Once again, though, this isn't the simplified version of that. This is considered the simpler version. Next, let's do 7 root 3. If what I just did made total sense to you, pause the video and try those two on your own. Did you try them? Did you get that this is the square root of 7 squared times 3, which is 49 times 3, which is, I have to think about that, 53 is 150, it's 1 less 3, that's 147. And 5 root 2 would be 25 times 2 in the radical, which is the square root of 50. Okay, cool. Now, number 10, same trick, but with cubes. So ask yourself what you do with that. Feel free to try it on your own. Pause the video and then wait, and I'll do it with you. Did you get them? Did you get that this one would be then the cube root of 2 cubed times 4? The only way this came out of the radical was if it was a perfect cube, and 2 cubed is 8, so this is the cube root of 8 times 4, which is the cube root of 32. This guy here would be the cube root of 3 cubed times 3, which is like saying the cube root of, what is that, 27 times 3, which is the cube root of 81. I think I did that right. Somebody might double check my arithmetic. And that's basically all there is to 4.3. So that was kind of short, so I thought we better maybe go into 4.4 a little bit as well. And for 4.4, oh, now I've got papers all over the place here. For 4.4, for example, and once again, they don't give me a whole lot of room in these examples to write stuff, but we're going to go back to what I said at the beginning of the last part of 4.3, where I said, let me flashback here, that radicals behave like brackets and like exponents. What do we mean? Why do they behave like exponents? Shock, they are exponents. Let me explain what I mean by that. For example 1, why don't we do, how about this? For example 1, let's simplify the square root of x times the square root of x. What would that be? Well, it's actually the same thing as saying, if you sign something by itself, it's like saying that it's the square root of x squared, right? Remember, anything times itself is being squared. And if you think of square root and squares as opposite operations, it should totally make sense to you that the answer to this is x, right? Like, for example, let's use an example with numbers. Suppose, pick something I know is a perfect square. How about 9? Square root of 9 times the square root of 9. Isn't that the same as saying 3 times 3, which is 9? So yeah, square root of x times the square root of x is x. I'm going to write it again. Root x times root x definitely equals x. That's a rule. That is a fact for any number in the universe. Even 0 would work for that rule. There's no exception for 0 on this one. That's a rule. Example 2 is also kind of a rule. Think about this. Simplify x to the 1/2 times x to the 1/2. Now you might be going, I've never seen exponents as fractions before, and if that's the case, don't worry about it. How about you just simplify this the way you learned how to simplify exponents back in grade 9. Back in grade 9, you were taught the product law, which we've actually kind of already seen today. What do you do with those two exponents according to grade 9 power law? Hopefully everybody's saying to their screen, you add them. And you're right, you add them, right? 3 squared times 3 cubed is really 3 to the 5, right? Because think about it, this is 3 times 3, and this is 3 times 3 times 3, so add them up, 1, 2, 3, 4, 5 3s, right? Remember that rule from grade 9? Okay, so apply it now. What's a half plus a half? And if anybody just said a quarter, give yourself a good hard slap, because a half plus a half is 1. So therefore, x to the 1/2 times x to the 1/2, I'm going to put that, is equal to x. Okay? And from this, we can make a conclusion. Notice that, let me get everything in the sights here. If this thing times itself is x, and this thing times itself is x, then these two things must equal each other. And like I said, radicals are exponents. The square root of a number is like saying, what is that number to the power of a half? Sometimes students have a very difficult time getting their head around this. Let me show you that this isn't as weird as it sounds. First of all, let's again go back to grade 9 one more time. Do you remember the argument for this rule? x to the power of 0 is 1. Do you remember why that's true? You can show that it's true in a couple of ways. First of all, I could show you that, for example, 2 to the 3 divided by 2 to the 3 is 8 divided by 8, which is 1. And I also know that there's a quotient rule that says that 2 to the power of 3 divided by 2 to the power of 3 is like saying 2 to the 3 minus 3, right? I subtract the exponents, and 3 minus 3 isn't 1, it's 0. So these two things must equal each other, or else the other rules must be wrong. And we know they're not wrong. Another good way to show that this must be true is to show that there's a nice pattern I can show you. 2 to the 5 is 32. 2 to the 4 is half of that, which is 16. 2 to the 3 is half of that, which is 8. 2 to the 2 is half of that, which is 4. 2 to the 1 is half of that, which is 2. Okay, keep the pattern going on the left. According to my pattern, the next number is not 0, it's half of 2. Half of 2 isn't 0, it's 1. And 2 is an arbitrary number. I could pick any base I wanted and play this game. We could play with 5s, 10s, pi, any number you like. As long as you don't start with 0, anything to the power of 0 is 1. And that's a weird little rule to get your head around, because you've always thought of exponents as repeated multiply. What does it mean to multiply a number by itself 0 times? Well, by the same logic, you could say, well, what does it mean to times a number by itself a half a time? But it doesn't matter, because these rules are true. That conclusion is logically true, and we can use it now. If you don't believe it, take out a calculator. It's kind of fun to play this game sometimes, right? The square root of 9 is 3. Take 3 to the power of a half. And you get, oh, whoops. Let me do that again. Take 9. I'm having button press issues. Take 9 to the power of 1/2, and you get 3. Same thing as if you go 9 square rooted. Some calculators even actually let you put in fractional exponents. I think this one does too. So let's try it. Let's go 9 to the power of, and let me enter a fraction. Those of you do know you have a fraction button on your calculator, right? 1/2. I actually honestly don't know if this is going to work. Oh yeah, it does. Yay! Fancier calculators can do it for sure. So there we go. That's kind of the main gist of this. And okay, so that's example 2. Now for example 3, I'm going to ask you to simplify 2 things. See what you think. Simplify these 2 things. Suppose I ask you to simplify x to the 1/3 times x to the 1/3 times x to the 1/3, and also simplify the cube root of x times the cube root of x times the cube root of x. Jot that down, then see if you can figure out what the answer is. I'll give you a hint. They're the same. Because this side, again, add the exponents. 1/3 plus 1/3 plus 1/3 is 1. So I'm not going to bother writing a power of 1. And the cube root times the cube root times the cube root, that's like saying anytime you times something by itself 3 times, it's like you cubed it. Which means that you cube rooted and cubed, those things cancel each other, and you get x. Therefore, this is my conclusion, and this is maybe the better version of this rule, because it works for anything, not just square roots. The nth root of x is like saying x to the power of 1/n. And that's the power rule they didn't teach you in grade 9, unless you were in the honors class. This is the fractional exponent rule. So an exponent of 1/2 is a square root, an exponent of 1/3 is a cube root, an exponent of 1/4 is a 4th root, etc., etc. And we can use that to evaluate. There's the one I just did in the calculator that I punched buttons on wrongly a second ago. This is like saying the square root of 9, which is 3. This is like saying the cube root of 125, which is 5. This one is like saying the square root of 4/9, which is 2/3. This one's like saying the square root of 0.49, which is 0.7. Aren't those fun? So you've now learned a new thing that you can do with exponents. You can use fractional exponents. I have no idea why there's all this space at the top of this page. I have nothing to write there, so I'm just going to keep going. Now, let's write these as radical. Oh, yes, yes, oh, yes, they did leave space here for a reason. Ah, okay, excellent. Extra rule here. Recall from grade 9 that if you have a power of a power Do you remember what you do with the exponents? Is everybody right now saying at their screen, you multiply them? Because that's right. It's x to the AB. You don't add them, right? If you have 2 squared cubed, that's like saying 2 squared times 2 squared times 2 squared, which would be 2 plus 2 plus 2, which would be 6. So this is fun. I'll just write the rule. I'll write the rule algebraically and see if you can figure it out numerically, which is kind of backwards from the way I did the rest of this lesson. If I have x to the a over b, it's like saying one of two things. You can write this two different ways. You can either say that it's the bth root of x to the power of a, or you can say it's equal to x to the a all bth rooted. Say what now? Let's do some examples. I can say that this is, and I'm going to do this two different ways. I can say that this is the cube root of 8 all squared, or it's the cube root of 8 squared. It doesn't matter what order I do it in. Isn't that cool? Try it. The cube root of 8 is 2. 2 squared is 4. 8 squared is 64. The cube root of 64 is 4. Haha! Isn't that cool? You know what? I'm actually going to maybe just put steps in there, because I'm sure that's going to blow some minds. So this is like saying 2 squared, which is 4. And this is like saying 64 cube rooted, which is 4. Okay, so isn't that neat? All right, 40 to the 3/5. I don't know what I'm going to do here. Do I want to do it this way or this way? Well, is 40 a perfect fifth root? Answer, no. My fifth roots, or my perfect powers of 5, would be 1 times 1 times 1 times 1 times 1, which is 1. Was that 5 ones? And then 2 times 2 times 2 times 2 times 2, which is 32. And then 3 times 3 times 3 times 3 times 3 is 243, so that's already too big. So 40 is not a perfect power of 5. But I can go, that's 40 cubed, and then take the fifth root of it. It doesn't matter what order I do it. Okay? So what is 40 to the power of 3? That's actually not that hard to do without a calculator. You're going, you'd make us do that without a calculator? And I'm saying, yes, I'd definitely make you do this without a calculator. Hey, do you know what 4 cubed is? Of course you do. We just talked about it. It's 64. So, right? 4, 16, 64. So think of that as 64 and then 10 times 10 times 10, right? Or, here, let me use a piece of scrap paper. It's like saying that I have 40 cubed is like saying 4 times 10 cubed, which is like saying 4 cubed times 10 cubed, which is like saying 16 with 1, 2, 3 zeros. So there we go. So it's like saying it's the fifth root of 16,000. Now, is 16,000 a perfect fifth root? I actually don't know. I was looking at these, I didn't look at this too carefully when I was doing my notes. I honestly am not sure if that is a perfect power of 5 or not. Let's use our calculator. Let's use our calculator. How do I find a fifth root? Well, can you see that? The shift on your power button? So I put 16,000 into my calculator, and then I go shift, this, and 5. And I have a feeling I'm going to get an irrational decimal here. I was right. 16,000 is not a perfect fifth root. But I'll bet there is a perfect fifth root in there. I bet that, remember my list? 32 was a perfect fifth power. Does 32 go into 16,000? Let's see. Oh, it does. So this is like saying the fifth root of 32 times 500, which is like saying 2 fifth root 500. Now, is this one of those cases where there's another perfect power of 5 hiding in there? I kind of don't think so, because let's see, let's make a list again. The perfect cubes, or perfect powers of 5 are 1, 32, and then 3 to the power of 5 is 243. 4 to the power of 5 is already, I think, over 1,000, isn't it? I think it is. I think it's 1,024. I'm going to double check. 4 to the power of 5. You betcha. So that's it. That's as simple as I can make that number. That one was cool. I enjoyed that one. Okay, next. I'm going to call this, let's see what, it's up to me how I call this. I think I'm going to call this one the square root of x cubed. Now you might be looking at that going, well, done, right? Actually, no, it's not. I could simplify that because I can think of x cubed as, wait for it, x squared times x. So that is like saying the square root of x squared times x, or times the square root of x, which is x root x. Haha! Cool! This one, I guess I'll call this the fourth root of w to the 5. And I could be, extremely uncreative and leave it like that, or I could want to simplify it and again think that it's the fourth root of w to the 4 times w, which is like saying w fourth root w. Teehee. Those are fun. All right. Write these in exponential form. So going backwards. This is like saying 3 to the 5 thirds. This one's like saying 6 to the 3 halves. This one's like saying x to the 7 fourths. And this is like saying w to the 4 thirds. All right, and that I think is the last. Oh no, there's still more. I'm gonna make one more point before we finish this off, but let's finish the examples. Okay. Actually, I can make that point right here in this example. So here we go. This will be good. Okay. One more time. What would you like to do first? This is either 4 cubed square rooted, or it's the square root of 4 cubed. Which one would you rather do first? Well, in this one, it doesn't really matter. Neither of those is very hard to do. But why am I allowed to do it in either order? In math, some things, order matters, right? 2 plus 3 is the same as 3 plus 2, but 5 minus 3 is not the same as 3 minus 5. Why does order not matter here? Because you can think of this as 4 cubed to the power of a half, which is basically that one. Or you could think of it as 4 to the 1/2 to the power of 3, which is that one. Now, why are those two things the same? Because in the power of a power rule, you multiply these together. And just using scrap paper here, 3 times 1/2 is the same as 1/2 times 3. They're both 3 halves. It doesn't matter which way you do it. Isn't that cool? So this is actually 64 square rooted, which is 8. Or this is the square root of 4, 4 cubed, which is 2 cubed, which is 8. Either way, the answer is 8. Now, look at this guy. Once again, I have my choice. I can either do the cube root of 27 to the power of 4, or I can take 27 to the power of 4 and cube root it. Which would you rather do? Tell you what, before you answer, what if I said you can't touch your calculator? Quick, what's 27 times 27 times 27 times 27? I have no idea. Quick, what's the cube root of 27? 3. This is my winner. So this is 3 to the power of 4, which is 81. I have no idea what 27 to the power of 4 is, and I don't care. I got my answer. I'm moving on. All right, this is interesting. This is like saying, again, I'm going to cube root negative 27 and then square it. Well, the cube root of 27 with a negative, you can't square root negatives, but you can cube root them. So this is like saying negative 3 squared, which is 9. Would it have mattered if I'd have done it the other way and gone negative 27 squared? No, except I don't know what 27 squared is, so I just did it this way. All right, this guy. I think I'm going to square root it first and then cube it again. So it's the square root of 0.01 cubed. The square root of 0.01 is 0.1. And then 0.1 times 0.1 times 0.1 is 0.001, right? Because think about it. When you times a number by itself and it has decimals, the number of decimals kind of adds together, right? Cool. I I think that's it for this lesson. Yep, that takes us to 4.5, which we'll do in our next lesson set. Thanks for watching. Go to your blog and check out which questions I assigned for you to practice this stuff.